So I'm Edward Davis. I'm the curator of fossil collections for the UO Museum of Natural and Cultural History, and I'm happy to be able to introduce Nick Famoso today. First, I'd like to welcome you to the annual Darwin Conversation Series. Each February, in celebration of Darwin's birthday, the museum brings you this series exploring species, ecosystems, and conservation. This evening, it's my pleasure to introduce our speaker, but first I'd like to call your attention to some upcoming events at the museum. On February 12th, that's Sunday, join us in celebrating Darwin's 208th birthday and his legacy of scientific curiosity with an afternoon of special exhibit talks and birthday cakes. The exhibit talks happen at noon, 1, 2, and 3 p.m. and are included with museum admission, and museum members are always get in free. February is volunteer recruitment month at the museum. From leading exhibit tours to helping with children's events, and even eventually helping in the fossil collection, the museum offers a variety of ways to get involved. Volunteer applications will be accepted throughout the month of February, so please either visit our website or see a staff person to apply or learn more. Finally, remember to join us next week for the second Darwin Conversation. Jack Sang will explore the evolution of dogs and help you discover what their fossils have to say about the adaptations we observe among living species. Jack's talk will be here in this room at 5:30 p.m., exactly a week from tonight. And now I'd like to introduce Nick Famoso. Nick is currently completing his PhD in Earth Sciences. He's actually my second PhD student. And he'll be finishing his degree in exactly a month from today when he defends his dissertation. And you'll get to see a preview of the dissertation research tonight. We are really fortunate to have him here. Nick left us early to go and become the chief of paleontology at the John Day Fossil Bed National Monument, which is a place that he has been working off and on since he was, 8 years old? So
something like that.
Nick is a homegrown Oregon boy, and it's wonderful that he's been able to get in this position and begin to help interpret the resources there for us. So, I'd like to say also that Nick is quite an accomplished researcher, having already published 6 scientific papers at this stage of his career. That's an outstanding number. So please, join me in welcoming Nick back to the University of Oregon.
All right. Okay, can you all hear me all right? Yeah? Okay. Thank you, Edward. I appreciate that. And thank you all for inviting me to come out all the way from not so snowy anymore Eastern Oregon. It was quite hairy trying to get over the pass today at San Em, but all the snow in the John Days is melted, and now we have a raging flood. So that's another thing we get to worry about out there. So all that aside, today what I want to talk to you about is evolution in the shadow of volcanoes. So what I will be talking about is a bit of information about the evolution of ecology, mostly of mammals. I'm a mammal paleontologist. I'm going to focus on mammals, and not just fossil mammals, but also modern mammals. Mostly deal with that, and then talk a little bit about some other things. I'll get to it a little bit later. We'll get started. So volcanoes in life, right? We all know volcanoes explode, and they kill things, right? Right up here, this is a... There it is. So this is one of the volcanoes up in Alaska, right? Just as an example of a nice Plinian eruption causing lots of problems. This is Spirit Lake up at Mount St. Helens, right? So what you can see here, lots of trees that are no longer living and a member of the community, living part of the community anymore. And that's direct effects of that volcanic eruption, right? It's pretty obvious. We know these sorts of things happen. And you might wonder, like, oh, well, yeah, volcano erupts to kill stuff. What exactly are you going to tell me about today? We know all that already. And you're right, we do know that. But what we don't know that much about is how things recover afterwards, particularly with mammals. We know more about that with other things, but not so much with the mammals. So what exactly does a volcano do when it erupts? It causes lots of different kinds of damage to the ecosystem, right? So a volcanic eruption isn't just an ash cloud coming out. There's a lot of different varieties to that. And even within a normal volcanic eruption, you can see a lot of different things. And I really like this graphic here that kind of explains some of the things that we have going on with a volcanic eruption. Most specifically, the things that we care the most about are the direct effects. So things like those pyroclastic flows, which are your fiery clouds of death that come in and kill everything, bury whatever's there, fry it, bake it, whatever. Then you have your fluvial deposition. Those are your mud flows, your lahars. Like that's a pretty major problem that happens with a lot of volcanic eruptions. And of course, lava flows. Lava flows do occur with a lot of different eruptions, but they're usually small, or in the case of the Hawaiian volcanoes, they're really not that fast to capture organisms, like living organisms, or sorry, not living organisms, all the organisms that are living I'm talking about, the ones that are mobile. So plants are kind of out of luck when it comes to lava flows, but a mammal, whatever, they're fine. But there's also things like scorching, toppled trees, and tree removal, and all of that has a pretty big impact on the ecosystem. You're pretty much wiping the slate clean wherever the volcano can actually reach, right? Some volcanoes are big, some volcanoes are small. And we'll talk about some of the variety of those in a little bit. But for an example, a volcano like Yellowstone, when it erupts, is going to have a much bigger impact because it's destroying more things than, say, Mount St. Helens even did. And that actually had a pretty major impact on a lot of things. So what exactly do we know? Well, we know that there's a long history between life and volcanic eruptions. Volcanoes have been erupting throughout the entire history of this planet, and life has only been around for a fraction of that time, but they've coexisted. And so life and volcanic eruptions have always had to sort of coincide, and life has had to evolve within the shadow of those volcanoes, if you will, for the entire duration of life history. Maybe not exactly where the organisms are, but it has always has had some kind of an influence. Right, most things die from the initial eruption, but what happens after is you get a lot of things coming back, and we know about that specifically with fish and birds and plants. And we can thank most of that to the work that was done up at Mount St. Helens. There's a lot of work that was done up there to study all of these organisms. Mount St. Helens was one of the first major eruptions that occurred in a place where there were a lot of people focusing on the eruption, right? It was in Washington, pretty close to Portland. You know, it was kind of important to see what was going on there. But prior to that, a lot of other eruptions were in a little bit more removed areas or places where there wasn't a lot of active research. And so Mount St. Helens helped a lot with that. And we also know that geography matters. So we know, like, you know, if you're in, say, the state of Washington, how things are going to respond to that eruption are different than, say, in Indonesia, right? There's different organisms. Biodiversity is a little bit different. You have different plants, a different amount of moisture in the environment. There's a lot of things to consider. And the one thing that we don't know that much about are my favorite things, the mammals, which is part of why I had a dissertation. So when I talk about evolution of volcanically disturbed areas, I'm mostly focusing on evolution in the sense of ecology. So how does the ecology change over time? And I really like this figure here because it's showing sort of the different types of ecosystems that you might expect to see in a volcanically disturbed area. You've got basically nothing, then you get some smaller plants that are, you know, live fast, or live hard and die fast, something like that. Basically the things that, and I'll get to this a little bit later too, the things that make lots and lots of baby plants and don't live for very long, the grasses, for example, and weeds, they show up first. And eventually that gives way to forests, again, with trees that are more long-lived. We can also talk about evolution in volcanically disturbed areas referring to morphology. So in this particular case, I'm showing some body size changes. You have your original population. You get an eruption right here, which is still going off as we speak. And the population may either get smaller, or it might get larger, or it might stay the same, right? So that's sort of like what we're talking about with morphology is shape and size, and I'll get a little bit more into that later. And then we can also talk about that reproduction, like what I was mentioning earlier. So there's two different groups. You have your K-selected things and your R-selected things. Basically what that means is things that live short time periods and produce lots of babies, like our mice, and then things that live for a long time and only produce like one or two offspring throughout the entire duration, which is like our elephants here. That changes depending on the eruption too. Like when exactly these different groups show up, the different type of reproductive strategies show up, is important for these volcanically disturbed areas as well. So volcano ecology. This is actually a field of science. It's a subset of disturbance ecology. And basically what you're doing is looking at, it is the study of the interactions between volcanoes and ecosystems, right? So it's pretty straightforward. You have a volcanic eruption. What does everything do before, after, during those various eruptions? And you can break it down a little bit. There's some different components that go into this. It's not as simple as you might think. So you have your ecosystem that was there before, and then you introduce your volcanic eruption. That's your primary disturbance. So this is your ash cloud, your fiery cloud of death is coming in and killing everything, or most things. And then it leaves a couple of legacies, right? So there's some organisms that are in places that don't get burned up, right? You've got like a little canyon that avoided all of the mud flows because of where it happened to be. All the animals in that area lived and were happy and fine, and there wasn't a problem with them. You get changes to the soil too, right? So if you can imagine, you get a bunch of ash, you mix it in with your topsoil, you're not going to have the same soil chemistry as what you had before. The organic matters are going to change in that soil too. So basically what happens from these eruptions is you get a new deposit, you get new topsoil, and some that's not even actually topsoil yet, and you have to wait for those plants and animals that live fast and make lots of babies to come in and change all of those new deposits into a new soil for other things to stabilize. And what happens afterwards, right, so you start getting more species showing up over time, and then your community gets stronger. We always want a stronger community. And eventually it starts to stabilize when there's enough players in the game, right? You know, when you're trying to make a proper community, you have certain roles you need to fill, and if you don't have all the roles there, you've got to, keep inviting new people to come into your community until you're at that particular level that you want. So this comes to specifically a topic known as succession, which is a fancy word that describes just the accrual of new species. You get new species showing up over time, and how fast that happens will change depending on the different eruptions. So the black line that I have up here, that's Mount St. Helens, and these are bird species as well. So you've got the bird species, the number of species here on the Y, and number of years post-eruption here on the x-axis. And here we can see Mount St. Helens. It's a pretty steep curve. It's doing pretty well. It's getting new bird species. It's all coming back. It's great. It's wonderful. Everything is working really well. Sirte, this is a volcanic island that formed off the coast of Iceland in the late 60s. And what's interesting with this one is you've got about 6 years where there were no bird species on it at all. So either that means that the birds just didn't know it was there because they're flying over the ocean and they're not always looking for a new piece of rock to land on to have their babies and to find food. But what it could also mean is that this was a completely new volcanic island and nothing was getting to it, so it took 6 years for there to be anything there to support new bird life, right? So we can learn a lot about ecology in these regions by looking at how these curves, how steep these curves are. And another thing to point out too is, right, Sirte is basically just below the Arctic Circle. There's not going to be as many species that far north as what we would see in Washington, for example. So that's where that geography comes in, right? Those are all very important things that we need to think about when it comes to these volcano ecology. So we study this with modern systems first. We have all of these volcanoes, right? These are the volcanoes. When I did an exhaustive search of the literature, these were the only modern volcanoes that I could find where we have done studies about, at least more than one study, about how organisms, communities, recover after volcanic events. And you can see they're kind of all over the place. We've got things in North America. We've got Iceland, Hawaii, New Zealand, Chile, Italy, Indonesia. It's all over the place. And there's a few more than this, but these are the ones that I really wanted to focus on. And so they're kind of all over the place, and a lot of these are islands, right? So Krakatoa, which is this one right here, is an island, right? And islands are going to behave differently than if we're, say, in Washington, right? Because your community is very limited geographically. It can't come from very far. But if you're in Washington, if you're on the continent, it's pretty easy for another population to come in and fill in a hole that was created by one of these eruptions. I specifically, as part of my research, focused on Mount St. Helens and Mount Lassen. You may wonder why Mount St. Helens and Mount Lassen. There's a perfectly good list of volcanoes up there. What was wrong with Hawaii? Why didn't you want to go do fieldwork in Hawaii? I would have loved to have done fieldwork in Hawaii, but unfortunately, most of my research didn't involve fieldwork, which is too bad. Mostly I spent my time looking at old dead mammals that were in a museum drawer for most of my research, as far as the modern things were concerned. But what's great about these two volcanoes is, one, they're both continental, so I can compare them directly, right? They're both in that same sort of environment. The ecology and the geography are a little bit different, but it's still more similar than if I was to, say, compare Mount St. Helens to one of the Hawaiian volcano eruptions. So specifically, I was looking at the Mount St. Helens eruption in 1980. That's the really famous one, and that's also where there's a lot of data. So another reason why I picked both of these was because there's data that exists for them, for as far as mammals are concerned, which is a good thing when you're trying to do science. You need to have robust amounts of data, and if you don't have that, then you can't really make good statements about the study systems that you're looking at. So with Mount St. Helens, it's well studied. Besides the mammals, there's a lot of other things, and when that eruption went off, we were really serious about studying volcanoes at that point, active eruptions. We became really serious about it. There's a lot of volcanic data. There's a lot of biologic data associated with it. And there's actually data for the mammals before and after the eruption. As you can imagine, it's good to see what was the population like before the eruption and what was the population like after. Compare them directly and see, do we have more species? Do we have different species? What exactly is going on, right? That's a good thing to tell. And we have basically about 5 years worth of good data. Now with Mount Lassen, which that eruption was much longer eruption, it lasted from 1914 to 1917, with most of it happening in 1916, if I remember right. The great thing about that one is that there is a wonderful mammal record that lasts from basically 1916 until 2010, I believe. So we get about 100 years worth of data, really close to 100 years. So we're looking at long-term timescales, which is something that we've not ever looked at with these volcanically disturbed areas before. Like what happens when you have an eruption on the long-term scale? Does it long-term change everything? One interesting thing about this too is that it's a smaller eruption than Mount St. Helens. Mount St. Helens had ash, it had lahars, it had all kinds of stuff compared to Mount Lassen. Mount Lassen mostly just had mud flows. So the footprint of this volcano is relatively small compared to what we have in Mount St. Helens. So that might be an interesting thing to look at too, is each volcano behaves differently, and it might be worth it to study different volcanic study systems to see how each of those different kinds of environments affects the ecology, if it affects it in different ways. But now I ask, how do we know that it really is the volcano, right? We've got, varying climates in varying places, right? Things change, times change. And how do we know it really is the volcano and not just say like the normal warming that was occurring at that particular time of that year? Like maybe it's seasonality. Like what exactly? Everyone was going out and sampling in the summer that year, and you get different species than the following year when they were looking at things in the winter, right? You might get different things there. So a way to try and control that is to say use a control system. And in this case, I used Mount Rainier and Mount Shasta as the controls because they were volcanoes that were outside of the path of devastation of Mount St. Helens and Mount Lassen, respectively. And they're both volcanoes in geographically similar areas. So you're going to be seeing similar organisms that are showing up in those two environments. So now we're actually going to get into some data. So this is Mount St. Helens. This is what the number of species is. So Chow here stands for the number of species, so that's richness, right? So we go anywhere from like 20, I guess that's 15 actually, 15 species here up to nearly 100, right? We've got quite a few species that we're dealing with here. And the blue line is Mount Rainier, that's our control, and the red line is Mount St. Helens, the one that we care the most about in this situation. So, and then on the bottom here is years. So we're doing a progression here. So if you remember back when I had that slide up that showed succession, right, and accumulation over time. Here's the eruption, right, and you're kind of getting a bit of an accumulation over time. And these are error bars here. So even though this one's lower, it may actually be more similar to this than the line makes it look like. So what it looks like we've got going on here is a general increase in the number of species that are being present, and then it sort of starts to stabilize, and it's almost back to the same level that we had before the eruption, right? So what we might be seeing here is some succession, but what's also interesting is that the Mount Rainier data is doing something very similar. So there may be succession going on here from the volcanic eruption, but it might also have some overprinting from the climate that was going on during this 5-year period. So there might be it might be more complicated than we might think, right? And so what have we learned just from looking at the number of species that we have? Well, there might be a short-term recovery, and it looks like succession, but there may be a little bit more influence of climate than we thought of before. Now we'll look at Mount Lassen. Mount Lassen's basically got nothing going on. There's nothing going on here. It is boring. As far as the ecology is concerned, it stays basically the same. One of the things I'd like to point out, right, you see these error bars for Mount Lassen are very short. And the reason why they're short is because the wonderful crew at the Museum of Vertebrate Zoology down in Berkeley had 2 pretty major surveys that they did that included thousands and thousands and thousands of specimens from both of those 2 points. So what we're looking at there is basically a general biodiversity survey, 2 general biodiversity surveys. And this one here is kind of funny because that's a huge chunk of time that's being represented, and it's mostly studies of bats and squirrels, interestingly. It'll be more interesting in a later slide. But so what's going on, at least between these 2 points, is yes, there's a decrease, but not a lot, right? And what I might have expected to see was a bit of an increase after this. And granted, this is a 100-year time scale, but definitely once you're at this point, what's ever going on here, it's basically just the signal of climate with this. So it's decreasing over time. And you can kind of back that up by looking at the Mount Shasta data. There's definitely a general decrease through the three time bins that I'm looking at here. Right, so the fauna appears to be relatively stable, right, if you take that climate into account. And obviously climate is playing a pretty major role. And maybe this volcano was just too small, right? So like I said before, it's just mud flows. So maybe those mud flows were just not enough to cause a long-term impact, right? It's not depositing huge amounts of ash, which would be changing the soil chemistry. So maybe that's something that's different with this eruption versus the Mount St. Helens eruption. Now we're going to look at everything together. This is a kind of a busy plot that shows a bit of similarity. So what you can kind of see here is there's 2 big chunks, right? This is California over here on the right, and this is Washington over on the left. So my initial hypothesis, well, I guess it wasn't a hypothesis, but it was more of an idea of, well, the Washington volcano should be similar and the California volcano should be similar based on the mammals there. I wasn't wrong. They definitely are more similar to each other than they within each state than they are between the states. And I'll start with Shasta and Mount Lassen here. There's that weird Mount Lassen eruption data set from 1930 to 1980, that middle one that's way different from everything else. Again, that's bats and squirrels. So general biodiversity surveys are really helpful with the sort of science I do, and these more specific things, not so much. But the cool thing here is that Mount Lassen is almost identical on this plot, right? So how close they are together is how similar they are, and they're basically right next to each other. and they're kind of close to Shasta too. So Mount Lassen, again, pretty similar, long-term, 100-year timescale. Mount St. Helens, on the other hand, is a different story. So what we've got here, this is the before the pre-eruption fauna. It's clear down here. And then you've got the post-eruption fauna up here, plotting more similar to what we see in Mount Rainier. So what we could be seeing here is you have an original fauna that was different from what you saw at Mount Rainier, and then the volcano erupts, and then the fauna is starting to get replaced by the communities that are nearby. So things are migrating from Mount Rainier and other volcanic regions to this region, and the fauna is just kind of changing, right? So what that means is scale might actually matter on these sort of time scales, and we see some evidence of succession. The change in players, right? That's what the last one was. These are the species that are present. We do see some change in the players, and we do see migration. So likely, or maybe, it is migration of neighboring populations to fill in the holes that were left by those other eruptions. Climate is still playing a big role, and what we were seeing with Mount St. Helens is kind of a quick turnaround. It's about 5 to 10 years before the fauna starts to just say, hey, we're back, we're strong, we're fine. Bring on another eruption, and we'll be back in 5 years, sort of deal. At least a volcanic eruption the same size as Mount St. Helens. If you get something bigger, it might be 10 to 15 years, or it could be 100 years. We never know. But like I said, that's only 2 examples. Can we look anywhere else? Well, we could just cause eruptions, right? We could go to a volcanically active area. We could just bomb it and cause an eruption, and then see what happens to the fauna, right? And this is a lovely picture from World War II. It's not a picture, sorry. It's an interpretation of what a plan might have been to deal with Japan. I wouldn't recommend that. Especially as a Park Service employee, I do not approve of the destruction of volcanoes with bombs. But what we could actually do, all joking aside, is we could try and wait for an eruption to happen. That could be a long time, and we're not able to predict those eruptions with enough leeway to know whether or not we're going to get good data, right? So we could go to Mount Hood, for example, and just kind of sit there and wait to see what happens, and we'd probably be sitting there for a really long time before anything would happen. We'd have a lot of great data from before the eruption, and we might never get data afterwards. Or we could go to a place where we know is more volcanically active, but then it could erupt while we start collecting, and we'd have like a half a year or a year's worth of data, which isn't going to tell us very much. Those are the problems that we have to think about when we work on data or work on questions like what I'm trying to answer here, right? Because we need good pre and post eruption samples. We can just examine volcanically active areas and see if that works, but that's not always going to be the most productive. And we can predict eruptions. I don't know if you remember from that earlier slide, but there are earthquake swarms that occur underneath volcanoes, and sometimes those can be used to predict when an eruption will happen, but that's not going to give you enough lead time before the eruption. So there's just not enough information that can be taken from that. And like when Mount St. Helens tried to erupt again in 2006, we kind of knew it might start, but we didn't know how big the eruption was going to be. Right? It could have been another 1980 eruption, or it could have been what it was, and just kind of a little bit of a release of gas, and not had any impact on the local environment. So, is there anywhere else we can look? Keep in mind, I'm a paleontologist. The fossil record. You actually can look at the fossil record to answer some of these questions, potentially. So just some examples. Yes, there are fossils that can be found in volcanic deposits. This is one of my favorite examples. It's a little hard to see up here, but this is the Blue Lake rhino. This is an exhibit that's up at the Burke Museum, which is probably not going to be up there anymore now that they're building a new building. But so basically, this is a rhino that was caught in a lava flow, right? So there's direct, this volcano captured this rhino. We know it was living at exactly the time when this thing occurred. So that's, we have things like that. Another one of my favorite sites, this is Ashfall Fossil Beds in Nebraska, which is a former Yellowstone volcano, which dumped about, I think there's 2 or 3 meters worth of ash in the beds where the 300 skeletons at this site are being preserved. So we can learn a lot about what happened during the eruption to these animals. There's a bone disease on these animals' bones. That was kind of a weird thing to say, but yes, there's bone disease on the bones that happened from ingesting so much of the ash that they had to live in, right? So we can learn about what happens to animals during an eruption. And then there's another couple of interesting things. This is a rhino skull that was preserved in one of those fiery clouds of death in Turkey. So we can find things like that. I didn't have a picture of it up here, but there is also a vulture that was preserved by one of the eruptions of Mount Vesuvius, where we could even see the little nictitating membranes in the eyes. It was so well preserved. That's one of the great things about these volcanic deposits, is that they actually are amazing vectors for preservation. They preserve so much material, it's ridiculous. And another place, which is near and dear to my heart, is John Day Formation. There's a lot of volcanic ashes in there, and it's also full of volcanically derived sediments, meaning that we're looking at evolution of these organisms within a volcanically active area. Where exactly is it, in case you've never seen it or know where it is? So we're over here in Eugene, and most of where I did my research was right here. This is the John Day Basin. My office is where that little red dot is, right there. And there's a few other distributions across the state, but that's primarily where we're looking. It's right on the cusp between what is considered central and eastern Oregon, on the eastern side of things. So that's where we are. And this is what the stratigraphy looks like here. This is sheep rock. This is probably one of the more well-known spots in the unit that I work in. That's what it was named for. And what we can see is all these gray lines here are volcanic ashes, right? So there's like 6 or 7 dated ashes in this section, or at least named ashes that have been more formally named, I should say. That's a lot of activity. This is 400 meters of rock. That's a lot of rock. There's a lot of fossils. There's a lot of ashes. And what we've got here is 31 million years ago to 25 million years ago, 26. So we're looking at 6 million years with 400 meters of rock, right? This is like amazing. This is so much material. There's so many fossils and so much stuff that we can tell from this area. It's ridiculous, right? Most other places have this much section with an ash here or an ash up there. And if it's lucky, 2 ashes, one on the top and the bottom. So we have a lot of really good constraint, but we also have a lot of examples we can look at as far as how do animals respond to volcanism, because there's all kinds of volcanism. And what I'll also point out that these things here, these land mammal ages, these are like suites of animals that are supposed to be there, the communities on more continental scale that are supposed to be there. So that's basically what those are representing. And one of these that I really want to point out is this big gray block right here with the red writing. That's the picture gorge ignimbrite. That's this thing right here. That big, thick brown layer that runs right through the middle of sheep rock. That is like 100 meters thick in places. This is a huge event. That is 1, maybe 2 eruptions. It's a very large event. It's a Yellowstone eruption size event that we have preserved here in Oregon. And it came from this little, not little, this big caldera right around Prineville. This particular caldera may actually be an early expression of Yellowstone. So what we might be able to see in the John Day fossil beds is one of the earliest expressions of Yellowstone, a volcanically active area that we care a lot about. So we might be able to learn a little bit about what this volcano may be able to do in the future by studying this eruption. So here's the John Day sequence here. So if you remember, there's kind of let me go back here a second. I don't like doing this, but all of these here, there's like an alphabet soup of layers. So you've got A, B, C, D, E1, E2, E3, F, right? And it goes all the way up. Those are the letters, and the way that, and each one of those layers sort of represents a geologically defined bed. And those are what I'm binning together to create the richness things that you're going to see here in a little bit. So the number of species, again, this is that chow again, number of species, and then each of these is one of those geologic bins. So this is A, B, C, D, E1, E2, E3, and I'm trying to represent the volcanoes that we have dates on with these little volcano cartoons here, with the picture Gorgic Nimbrite being the very large one because it was a very large eruption. And what's interesting is through most of this section, nothing's happening. And maybe what that is we're, these are huge time scales, and we're looking at like tens of thousands of years here, so maybe the ecosystems are recovering pretty quickly after the event. As far as species richness is concerned, how many species the community can have, maybe there's an impact from taphonomy, which is basically like how things break down over time mostly by scavengers or by other factors. But what's interesting is that we see from before the picture Gorgic Nimbrite to after, there's a little bit of an increase. But another thing to point out is this error bar is huge, so we don't really know what's going on there, right? There's just not enough data to really say something definitively. But after this, we kind of start seeing a little bit of an increase with the number of species. Not exactly sure what's going on there, why that's there. Might be from the volcano, might not be. So then I did that similarity thing again, and what's interesting is all of these layers, so this is that alphabet soup again, and it kind of looks like a soup right now, but all the things here, those are the rock layers from before the ignimbrite, right? So what that is sort of suggesting is that all the animals before that huge eruption, or all the period of time before was pretty similar, and then after the eruption, there's some weird stuff going on, right? It changes. The fauna are different. And the reason why they're split the way that they're split, I'm not entirely sure. It's probably taphonomy, but there is a difference. There is a distinct difference here between pre and post-eruption. So who are those players that we're talking about, those different species that might be causing the fauna to be different? So what I've done here is I've broken these down into families, and I hope that you're able to sort of get an idea of what's going on. The red line here is the picture Gorgic Nimbrite, right? And each of these, this is abundance, right? So the fatter the line is in this direction, the more, the larger part of the community it was. So there were more of these hypertragulids, which a hypertragulid is a little mouse deer. They're pretty cute and adorable, except they've got these huge fangs that might be a little intimidating. There are very similar things that live today. They didn't use the fangs for killing things, I promise. They were herbivores. So what you can see here is they're pretty abundant. And then the eruption happens, and then they tank. And same thing with the oreodonts. These are these sort of camel, pig, sheep things that were on the landscape. And they are doing pretty well, and then they just kind of drop off. The dogs, too, that's this row here, the canids, which we may learn a little bit about next week in Jack's talk. They're doing pretty well, and then their diversity tanks. And they just kind of cruise for a little bit here. Horses do something very similar. I love horses. My first research projects were all on horses. And I was very sad to see that even though they are a smaller part of the community, they still tank and basically disappear at various points in this area. The one things that are getting bigger are rodents and lagomorphs, right? So there's higher diversity there for, and I'm smiling at one of my other advisors because she works on these things. But we see more gophers, we see more aplodontids, which are the mountain beavers, and we see more rabbits start to show up. Now, one of the things I want to point out with that is, where do gophers and rabbits tend to live? They tend to live in open habitats, grasslands, right? Or not necessarily grasslands, but at least not where there's a ton of trees around, right? And these other organisms like mice deer, they prefer to live in more foresty sort of environments. So there are some indicators that maybe what happened after this eruption was an opening up of the habitat. So sort of a more entertaining way to picture this is if you imagine this is your ecosystem before the picture-gorgic nimbrite. You've got your, these are the oreodonts that we had around there. They don't really look that sheepy or piggy or camely in this particular image, but that is what they are, I promise. We've got dogs. There's a large variety of dog species. I think there's like 6 or 7 species of dog that are present at this period of time. It's amazing. We've got rhinos. We did have rhinos that were around. This is the mouse deer. You can kind of see there's a little bit of a white thing there. That's its little fang. These entelodonts, which are sort of omnivore, carnivore sort of things, are mostly omnivores, but I wouldn't put it past them to maybe eat something that's close to death. Beavers are sort of there. This is a cool thing called a clawed oreodont. So this one is suggested to maybe prefer habitats with more trees. And then this is our mountain lion-sized nimravid, which is a false saber-toothed cat. And so all these things are present before the eruption. And this is what the fauna looks like immediately after the eruption. So in the rock layer right after the picture-gorgic nimbrite, you see beaver, oreodont, 1 species of dog, rhino, and these hypertrags. And why that might be is maybe because these were more robust, there were more of them, so they did a little bit better job of surviving. And then the following geologic unit right after that, you see a bunny start to show up. There's more rabbits. Cute little rabbits are there. And then the horses come back another layer after that. So yeah, things are changing quite a bit. So what did we learn? So maybe the size of the volcano really does matter, right? This picture-gorgic nimbrite is huge. It is an amazingly large eruption, and that may be something, it may have been large enough to actually cause a major change in the environment, right? Unlike all those smaller ones, because we were looking at all those smaller eruptions, and nothing really changed that much, I should say. But climate still is pretty important. I'm not able to really rule out climate as a factor for why these communities are changing. That big change may just be coincidental right at the picture-gorgic nimbrite. It's hard to tell. We need more data to be absolutely certain about that. So then, briefly, a little bit about the morphological changes. We talk about shape and size. I did a study where I looked at the horses in the John Day Formation through time, trying to see if across these volcanic boundaries anything changed in size, shape, or the wear patterns on their teeth. And what I found, missing a slide there. Oh, no, I'm not. Helps if I remember what my talk is. Before I get to the body size, I just want to talk about some characteristics that we do see in some fossil taxa that occur in volcanically active areas. So South America has a ton of volcanic activity throughout its history. Right? The Andes have just been going off for a very long time. It's been causing a lot of change. So there's some suggested adaptations to that ash. It may not be directly related to the volcanic activity, but there has been suggested, and I wanted to present that to you as a suggested hypothesis for why these characteristics exist. So this is a horse that existed in the Plio-Pleistocene, so we're talking about the last 5 million years. And you see this bone right here, this is the nasal, the nose bone. This is what's called retraction. So it's really far back, and other organisms that have that are things like tapirs and elephants. So things that have trunks. It doesn't quite look like this in those 2 groups of animals, but what the reconstruction is a bit of a muscular lip. So it had basically something like a prehensile lip that it may have been able to use to grab stuff. And why might that be important in a volcanically active area? Well, you've got a lot of dust, right? There's that ash that's getting deposited on it, and maybe you don't want that on what you're eating, so you may be able to, say, manipulate what you're eating in a way to get rid of a lot of that. There's also some suggestion that a group of baboons in Africa were doing exactly the same thing because they are eating grass and they have teeth that look, well, they don't look like ours, but they have short crown, low crown teeth like ours, which could wear away really fast in the presence of grit, hard material. And that brings me to the high-crowned teeth. This is a South American organism with fairly tall teeth. And one of the other things that I like to point out too with the horses, because they also have these high crown teeth, a horse's tooth goes clear up here in the skull, right? That's part of why the eye is so far back in a horse, is to avoid having the tooth sort of in the way. So horse teeth, right? My horse's teeth, when they were full-grown teeth, were about this big. And a lot of that is suggested to be an adaptation to dealing with lots of really hard stuff in your diet, right? If you've got sand, like think about chewing on sandpaper for your entire life, you're not going to have teeth for very long, right? So you need taller teeth to deal with that, and this might be an adaptation to dealing with that. And this is a phenomenon called hypsodonty. Some rodents take it even further into a thing called hypsilodonty, where they have ever-growing teeth. But this is common with the larger ungulate mammals, and it may be something that we see in ungulate being hoofed animals. So this may be something that in South America was forced to evolve a little bit faster than what we see elsewhere because of the volcanic activity. Now we're going to get to the John Day Formation and what I was seeing there. So basically the picture gives it away. There was no change in the size. And that's kind of interesting, right? Because we might expect to see smaller things because there's less resources available right after the eruption, so maybe the species would get a little smaller. But we don't see that. We also don't see any change in the wear patterns, which wear is a direct, what your teeth, the shape of your teeth are directly related to what you eat. And if you're eating a lot more ash, then maybe your teeth are going to be, have more wear on it or wear differently. There's been some other studies that have shown that in drought conditions, wear looks very different, right? We don't see any of that with these animals. So what I suggest here is that maybe migration of other populations from outside of the volcanically disturbed area was more of an influence on the evolution of this horse than the volcanic eruption itself. Which is why I'm saying migration is maybe stronger than the natural selection or the selection that is caused by the eruption itself in this particular event. And then I'm just going to talk a little bit about reproduction. We're getting kind of close to the end here. So R and K selected things. R selected basically means things that reproduce a lot, make a lot of babies, live short lives. And then the K selected things, again, are your elephants and things and organisms like us that produce few offspring relative to their lifespan. And why that's important is these guys require way more resources to survive than these guys. So in a volcanically disturbed area where you have virtually nothing compared to what compared to a normal ecosystem or not a normal ecosystem, the ecosystem before the eruption, it's better to be able to do this, right? And then the behavior of these organisms starts to stabilize the soils and create new soil for the more long-lived things to be present. And we do see a bit of this. I haven't gotten a lot of data on this yet, but I'm working on it. But there is data to suggest in Mount St. Helens that we see a lot more rodents and open habitat taxa that produce a lot of babies showing up first, and then they're getting replaced by these larger animals. So remember, we were seeing increase in the number of species, but there's also a bit of change in the players themselves where you have more of these rodent-like organisms, things that fill that sort of role as an R-selected taxon showing up first, and then giving way to these bigger, more long-lived taxa. So you wouldn't necessarily see a change in the number of species, but you would see a change in the similarity between the two sites. So conclusions, volcanoes produce an amazing fossil record. I just want to reiterate that. Come and see some of that fossil record at John Day Fossil Beds. I promise you will not be disappointed. The scale of the eruption matters. The bigger the eruption, the longer it takes to stabilize is sort of the suggestion from the data that I have. There is this succession. It occurs, and we can see it in a variety of study systems. The migrant populations will probably play an important role. The morphology is complicated. There are some adaptations, but they may not be because of the volcano, and body size may be influenced by the migration that I mentioned earlier. And then reproduction is a little bit more straightforward with more quick, fast-living things showing up first and being replaced by more long-lived things. So I have these acknowledgements here, and before I'm done, so I want to thank all these people, including the University of Oregon and everybody else, and before I forget, we have a volunteer opportunity at John Day Fossil Beds. So we have this wonderful eclipse that's happening. You may have heard about it. We're expecting a ton of people to show up in Eastern Oregon, and just sort of as a reference point, the county that I live in out there has about 7,000 people, and we're expecting about 50,000 people to come into the area. So I have some wonderful flyers here. If you're interested in coming out to John Day and spending some time with us during the week of, well, not the week, but between August 16th and 22nd, we could use some volunteers, and you might be able to get some free housing out of some tents or RVs. It's the best we can offer. But if you're interested in that, I've got some flyers up here with the contact information. And with that, I am done. Thank you very much.
Thanks, Nick. I'm gonna let you call your own shots with the Q&A. So.
Okay. Okay. Does anyone have any questions? Yes.
So we did a written record in Europe and even in Asia. There are those mega explosions that change the Earth for a year, even 2 years.
Right.
So with smaller eruptions, or even the mega eruption to begin with, how would you see that through a fossil record?
Right. So that's one of the hard things is we're really only able in the fossil record to look at recovery from where there is evidence of the eruption itself. Right. So there could be. Right, because one of the other problems that you have if you're looking at, say, like an eruption like Toba, for example, which is an example I've used in talks like this before. Toba has, that one's an interesting one because the ash from that mostly fell in the ocean. And we're not able to see a lot of anything from that. And the one study that I know of that happened in Toba, there's a great fossil record before the eruption. And then after the eruption, so you've got 77,000 years ago, the next data set that they can use is the modern data set. So that's one of the problems that we have with some of these data sets too, is you've got these huge time ranges, and either the record is really great right after the eruption, or the record is really great right before it, but never on both ends. And that's where places like Mount St. Helens and the John Day Formation are really important for telling stories like this. But yeah, no, you're right. In a situation like that, it would be really difficult to tell, especially since the nature of the fossil record doesn't always give you exactly where that event occurred. So if you were looking in North America at that time when that eruption happened, there's not going to be any ash there to tell you, and there may not even be any fossil record there depending on where you looked. So it really depends, and that's why I try to focus on places where we know there was an eruption because there's direct evidence that it happened there. Yeah.
I have a question about your North American versus South American observations.
Mm-hmm.
So I'm wondering if there are any known historical geographic barriers that would have prevented that migration in your normal South American borealis versus
right.
what you saw with migration.
Yeah, and I'm actually, that was something I was thinking about while I was making that slide. I was like, man, why is it that we see more of it there than we see up in North America? And really, so I'm going to do a little bit of, arm waving here. But so the best that I could tell is, you have a slightly smaller geographic area generally than what you see up in North America, and it's also isolated for a lot longer from the rest of the globe. South America tends to be there isolated for a lot longer. However, the taxa that I'm showing here, so that the one taxon, the skull that was on the left, is an endemic South American thing, and it's there for a very long time, and it evolved in place. That horse, on the other hand, showed up like 5 million years ago, evolved really quickly. It had immigrated from North America, evolved, changed, developed the trunk, and then was its own thing, a South American horse, and then eventually remigrated back up to North America. So there might be some geographic barriers like that. There's also we'd have to look at where the forests versus the plains were during the time when these organisms were evolving. And I'm sure actually Greg would probably have a better sense of that than I would. But it would depend on where exactly those forests are and where the habitats are, because these horses and other ungulates that are evolving in those areas are probably going to be preferentially in the grassy areas than in the foresty areas, more often than not. So that may also be another geographic boundary, is just where the habitat was. Yeah.
Reference to Yellowstone volcanic event.
Yeah.
What does that mean?
Okay. So, right, Yellowstone, right, we know is a hot spot, right? So there's a plume of magma or whatever it might be. It may not be a plume, whatever. Ask another geologist. There's an ongoing debate. So basically, there's a hot spot underneath the plate right there, underneath Wyoming, whatever other states are over there. I'm forgetting which states are bordering right where it is. Montana, there you go. I lived out there. I should remember this. Right, so you've got this plume that's underneath that, and it's cooking the rock, right? But it's sitting just there, and the plate's moving over it, right? So it's building up a lot of heat and magma and pressure, and when you get heat and pressure and magma building up like that, you have the potential for a large eruption, right? And this isn't going to erupt like Mount St. Helens. This is going to erupt more, it's a caldera eruption, and this is like a 50-mile wide thing, and it just has little mini volcanoes showing up all over within the area, potentially. So that's this type of eruption that we're talking about, but we find evidence of that throughout the entire history of Yellowstone hotspot, right? There's a nice track of volcanic centers of calderas that basically runs through the Snake River Plain and sort of starts to get diffused once you get to Oregon. But so when you go to the Snake River Plain, most of that big curve is full of calderas that used to be Yellowstone. And we find evidence of those eruptions all over North America, including ashfall fossil beds that I was talking about before. We can trace that back to the Bruna Jarbidge eruption, which is in southeastern Idaho. And we know it's from that because we chemically fingerprinted it, and we know it's from that spot. And we can tell, man, that thing went off and sent ash clear out into northeast Nebraska, and it was not where there was a watering hole, but in general, this thick, right? It's about over 1,000 miles away, and it's making a deposit like that, right? So that's the sort of magnitude scale we're talking about with these sort of eruptions.
And I heard you say the Prineville caldera
Yes.
is related to that
It's
movement.
yeah. There's some data that suggests that eruption, that caldera may have had the same source as the Yellowstone hotspot, or something similar to it. It's at least a hotspot, like Yellowstone, if not the same hotspot.
Thank you.
Okay. One more question? Yeah.
So regarding the John Bay area itself, with
Yes.
all those layers of goodies
Yes.
there, I mean, are there constant waves going on?
So the way most of the paleontology works out there when we do paleo field work is it's constantly being eroded. So we've got these steep slopes that are actually the most protective ones are about 15% gradient slopes. And erosion happens, and it also happens to be more frequent on the south-facing slopes. But so it's just eroding, and the rock is washing away, and it's exposing whatever bones are present there. And so these things are just sitting on the surface and rolling down the hill. And often will get destroyed because of all the weathering that's occurring while this is happening. So my field crews go out pretty frequently. Not right now because there's been so much snow and ice that it's not really worth it to go out into it. But typically in the summer we go out like once a week or once every 2 weeks, and we just kind of go and we do what's called prospecting. We just kind of walk over a slope, find some stuff, collect it, bring it back to the museum. And occasionally we are able to dig things out of the ground, but it's much more point source thing. So we'll say find an Oriodont skull that is stuck in the middle of a wonderful outcrop, and we've got to go out there with a field crew and spend many, many, many hours digging it out of the ground and take it back to Eugene. in the case when I was a graduate student here. We take it back here. I was thinking of a very specific example of that. And those sorts of things happen pretty frequently, but it's not like it's we don't go to a site and just start digging. It's much more of a exploratory sort of situation.
Oh, I think we need to
After.
close up, but you can come out.
So, if you could emphasize, how long have they been collecting?
Oh, that's a good point.
Localities, and what is the diversity levels that we have in Oregon compared to elsewhere?
Right. So collecting in the John Day Formation, 150 years. Thomas Condon, our well-known former faculty member, was one of the first people to start collecting out there 150 years ago. And right in the Turtle Cove member, that green stuff that I'm working in, there's like 98 different species that I'm dealing with, which is a huge amount of fauna. Most other places are lucky to get, 20, 30. So yeah, it's pretty cool.
Amazing. You should go visit. Let's thank Nick again.